Welcome to the second lecture in this series on net zero. What I want to do now is to turn away from the overall framework and the 30 wasted years that we've had since 1990, the failures of Kyoto and the implausibility that the Paris process will produce a result consistent with 2 degrees, let alone the 1.5 degrees that was added as a more stringent target back at those Paris negotiations. And I want to turn to the key sectors that are responsible for all that carbon up in the atmosphere. And although there are lots, 3 have to be cracked. That is energy, transport and agriculture. Between the 3 of them, that's probably 3/4 plus of the global emissions. And if we don't crack each and every one of those, net zero becomes a platitude and a nice idea sometime out in the future, but we'll carry on in the same mode as we have for these 30 wasted years we've had so far and make little progress. Now, most of the attention today has been on energy and in particular on electricity, and there's a very good reason for that. And that is that everything else and its decarbonisation in large measure depends upon what happens in electricity. And so this lecture's all about decarbonising electricity. If you don't have low carbon electricity, what's the point of trying to have electric cars? What's the point of having a approach to agriculture, fertilizers and so on without low carbon electricity? Now I say electricity because that is the way in which over the next several decades we're going to consume our energy more and more. And the reason for that is not just the inherent advantages that electricity has, and which we're all familiar with and indeed can't live without, but it's also the direction of the economy more generally is going towards an electric future. Just think out on the economy 20, 30 years ahead, the one that we're supposed to be moving towards net zero for. What will it look like? Well, it's pretty clear that almost everything will be digitalised in 20, 30 years' time. The communications revolution has only just begun, and as it unfolds, it will bring about the Internet of Things, and almost everything will become effectively data-driven, Internet-enabled, and hence pervasively digital. Robots, think 3D printing, think artificial intelligence and so on. So there is a wall of additional electricity demand on its way, and the reason why a digital economy is electric is because that's how you make digital stuff work. It's pretty hard to drive a digital economy directly on coal, oil or gas. You have to go through this intermediary step, and that enables the digits in a digital technology to be operational. Now, it's not just that a digital economy is more electric, and therefore we're going to have more electricity in our energy mix going forward. It's also that a digital economy relies upon greater and greater security of supply. Think back to the 1-hour power cut in the UK in the middle of August. What that power cut demonstrated, apart from the inadequacies of the way in which the system is currently operated and the failures of the capacity auctions to deliver sufficient capacity of a firm variety to meet the requirements. In addition to that, it demonstrated that just knocking out the electricity, even for a short period, brings everything cluttering to a halt, including the transport systems. And what does that mean? It means that there's not much point in trying to digitalise and decarbonise those sectors if the electricity is not secure. So we need more electricity capacity than we otherwise would have done, because security is more important, and then much of the decarbonised energy sources in electricity are intermittent, and therefore we need more and more backup. So the shape of the electricity market going forward is higher demand and more security. And then, of course, there's all the additional stuff on top. For example, with a good dose further of global warming, we're all going to want air conditioning. Think of the extra demand that creates on top of the demands that come from all the videos, the video screening, the bitcoins, and all the other products that come out of our internet revolution. So the demand for electricity is going to go up, and we're going to have to decarbonise that, come what may. And what we then have to think about is, what are the cards we've got on the table already which might help us to do that, and do they add up to enough to get us to net zero, both domestically and globally, so on a net zero carbon production and a net zero carbon consumption. So let's just take a look at the options that are in front of us. If you read the popular press and if you listen to quite a lot of commentators, you will be led to believe that if we just fit enough solar panels and bolt enough wind farms down, particularly onshore as well as offshore, that all will be well. We're told each wind farm is enough to power, say, 60,000 or 600,000 homes, and we're told similar numbers about how many houses can be powered by solar panels. Well, the truth is that those numbers are largely PR. The reality is that wind does not work 50% of the time, and solar does not work at night, and we do not have enough storage to make those technologies move from being intermittent to firm power. We are on our way to improving that position, but anyone who believes that existing solar and existing wind are going to crack our net zero problem in electricity needs to do a little bit of hard practical arithmetic and look at how decentralized and disaggregated and low density these energy forms are. It's easy to make progress and to announce, for example, that on a particular day 40% of our energy was from renewables. But what you really have to make progress on in renewables is the backup, the support, the storage, the batteries, the standby generation, etc. And it's on that side, plus active demand management, that the technological breakthroughs are going to have to come if those renewables are going to be more than a part solution to our problems going forward. So renewables, yes, of course. Current generation renewables, helpful, but not sufficient. What we really will need is next generation renewables, and that's all about science. That's about opening up the light spectrum. That's about new solar film and new materials for capturing solar power. And yes, some more efficiencies might come out of the wind farms, but the technology is inherently limited in a way that the solar side probably isn't. And more batteries, more storage, more active demand, more smart grids, more smart meters, all that kind of stuff. And we kind of know what that agenda is, but we have to bear in mind that every penny that's spent on current renewables is money not spent on the R&D necessary to develop the new ones. And we shouldn't be sold the illusion that this is all going to work just as it is on the current projection. Now that leads people to say, well, okay, if renewables won't do it, how about nuclear power? And particularly, how about nuclear power plus renewables? So you have to say, when you look at the costs of nuclear power, that there are problems about those costs. There are problems about delivery. There's problems about the safety of the nuclear waste and its protection and treatment. And of course, there's public perception and whether or not the nuclear industry likes it, the link between a domestic civil nuclear program and the military use of nuclear technologies for nuclear weapons and so on. There are lots of obstacles, but let's just start with the cost. It's said for example, that Hinkley is hideously expensive at £92.50 a megawatt hour for a long period of time. Well, it is very expensive because we've used a very bad model for developing Hinkley. The British government's approach has been to try 3 different reactors and 3 different financial packages and try and see which one works, rather than going for a series production of one technology and a serious supply chain approach. It's pretty hard to make it more expensive than the route that's been taken for nuclear in the UK. But even at £92.50 a megawatt hour, let's remind ourselves of the comparisons. So biomass, turning Drax into effectively a large log burning stove, is 105 £105 a megawatt hour for stuff that is, of course, somewhat better than burning coal, but not a particularly low carbon result. If you compare carbon with carbon from renewables to biomass, renewables is better than the £92.50 versus 105 that's out there. If you compare it with offshore wind, it's interesting again. We're told headline after headline that wind is coming down towards £50 a megawatt hour. Yes, that's the price that's being bid in the market, and it's a great success that those costs have come down. But of course it's not for firm power, and it's not for the equivalent firm power type auction which I set out in the cost of energy review. So if you do a like-for-like comparison and you finance nuclear power an altogether more sensible way, which is broadly around the regulatory asset-based model, then it's not at all clear that offshore wind is cheaper than nuclear. And remember, nuclear is large-scale continuous supply, predictable supply, whereas offshore wind depends upon the wind, and of course solar doesn't work at night. So on the nuclear side, there's no doubt it could make a difference. It's no doubt that a real attempt at net zero by 2050 without nuclear power is going to be very tough, as the Germans are discovering, having decided to exit even the existing nuclear power. But it's also clear that there is widespread public disquiet about nuclear. There are big problems that can't be avoided in the construction processes, and it's not clear that small modular nuclear and new innovations are going to make much difference anytime soon. So that's renewables plus nuclear. What else could we do? Well, the alternatives then turn to CCS, that we could burn gas and even burn coal, but extract the carbon from that burning process and then bury it underground. Well, you have to accept, first of all, that CCS is in itself an admission of failure. It's a failure to mitigate, reduce, eliminate the emissions in the first place, and so we're left with trying to clean up the mess afterwards. So it is very second best. It's also true that most of it so far has been used for oil-enhanced recovery. In other words, to push gas into oil wells to get more oil out and therefore, ironically, to burn more carbon. It can be done. I don't think there's any doubt about the physical possibility of doing so. And the UK has a lot of empty or depleted wells in the shallow water of the North Sea and pipes connected to them. So if anywhere is going to try CCS in the world, then the UK is the obvious place to go for. But don't delude yourself that this will get us to net zero, or that there won't be very high costs associated with this. That's why the oil and gas companies, despite their need to find a route to, quote, surviving in a net zero world, have been reluctant to put their own money in substantial amounts where their mouth is about the future of CCS. And then there's the volume effect. Is it really the case that we've got enough holes in the ground to bury enough CO2 to really hit that net zero? And my take on CCS is that what CCS is really useful is what you do on top of the decarbonisation of net zero and try and put right some of the emissions we've made in the past because the Industrial Revolution has contributed a lot. Now, there is one other form of sequestration, of course, which I'll come on to in the lecture on agriculture later on, which is natural sequestration. And natural sequestration is using putting carbon back in the soils and planting trees, and I'll come on to that later. So that's the next option. What else could we do? Well, we could try and get out of jail by buying offsets abroad, including those offsets for planting trees, etc. We could buy the electricity from abroad, which we do already in significant amounts, and hope that it comes from, say, nuclear power stations in France rather than coal stations in Germany. We could do some of that. And there's nothing wrong with trying to find the cheapest places on the globe for reducing emissions. But it's not really a solution to net zero, and it's not really a free card that we could use. So all of this then comes down to cost. And one of the great myths that some environmentalists have put forward and is at the forefront of, say, the Stern Review, is this idea that doing this is going to be cheap. You know, it's only going to cost 1 to 2% of GDP, and hey, that's a long time in the future, and there are all these industrial opportunities coming down the track, and so we're all going to be better off. Really? Is it really true that we can have wind farms and solar panels and nuclear power stations and our costs go down and all this extra demand for our digital economy? Well, no, it's not true. And in the Cost of Energy Review, I set out just how big already the legacy costs are of decarbonisation. And remember too that there's a good reason for believing, and in my burnout book I set this out, that the fossil fuel prices are going to go down and go down a lot, making them more and more competitive. The real truth about the costs of decarbonising electricity is they are going to be expensive. And when you add carbon consumption to carbon production and take the energy intensity of the imports into account and the coal that backs them, then you'll observe that the sort of carbon tax that we required as perhaps the most efficient way of achieving the objective will be very hard. And that brings me to the global dimension of this. It's always going to be a good idea, in inverted commas, to decarbonise electricity. And that makes sense if there's a carbon border adjustment, so we don't simply displace British industry by closing it down with higher costs and it moving abroad and we're buying the imports from countries like China. And that's why the carbon border tax is so important. But have in mind that global warming is a global problem. And if you look at the what's happening at the global level, just bear in mind that China is big in this story, as is India, as is in Africa. China's building another 250 gigawatts of coal to add to its 1,000 gigawatts it already has. It's financing anything between 200 and 700 coal plants abroad down the One Belt, One Road path. Coal in 240, even with all the new energy policies in the IEA scenario, is 25% as opposed to 40%. You might think that's good news, but 25% of a much bigger world economy is a bigger coal burn than 40% of today's economy is now. So there's a huge amount of coal coming. The border issue is very important, but within that frame, we have to get serious about the next generation of renewables in order to make sure that we can do this bit of net zero carbon. And that will leave just two other areas to address, or two main other areas addressed, which I'm going to do in the next couple of lectures. Transport next, and then agriculture. Thank you.